Hello everyone, Assalamu alaikum. I am Rubab Ahmmed, Senior Lecturer, Department of Tripoli, European University of Bangladesh. The title of my paper is Optimizing Hybrid Power for Manpura Island, a case study in Bangladesh. My abstract ID is IMCCRT 20234083. The presentation synopsis is introduction, objectives, methodology, optimal location for hybrid power plant, monthly average solar GSI, wind resource analysis, load profile for different households, monthly load profile, schematic of hybrid power plant optimization result, monthly electricity generation, solar PV system output, wind turbine output, generic biogas generator, hydrokinetic output, conclusion and references. Introduction. The hybrid power generation system is a hybrid combination of two or more natural resources to gain the full potential of renewable energy. The hybrid PV, wind, biomass and hydrokinetic system is combination of wind energy, PV energy, hydrokinetic energy and biomass generator used to generate power from each other. The Homer simulation process for the hybrid system gives us a clear idea about determining the optimized result on a specific location for the available natural resources present in the region. The main objectives of my paper is to analyze the energy load for the chosen region, to analyze the feasibility of implementing a hybrid renewable energy system in a residential setting, including factors such as cost, energy efficiency, and environmental impact, to examine the potential benefits of hybrid renewable energy system for homeowners, including cost saving, energy security, and sustainability, to evaluate the performance and effectiveness of different renewable energy technologies in a residential setting such as solar panels, wind turbines, and biomass generator, to develop recommendation for homeowners considering a hybrid renewable energy system, including guidance on system design, installation, and maintenance, to explore the potential for scaling up the use of hybrid renewable energy system, the residential settings, and identifying any challenges or barriers to wider adoption. Methodology. Identify the location in Manpura Island where it is most feasible to construct a PV, wind, biomass, hydrokinetic hybrid power plant. Collect the PV wind energy data necessary for proposed system from NASA surface meteorology and solar energy for a specific location. Design and simulate the hybrid system for the selected location with the resource inputs. Determine the optimal component configuration and evaluate the proposed model. Optimal location for hybrid power plant. The optimal location for the hybrid power plant should have proper solar exposure, sufficient wind energy to regulate wind turbines, and proper biomass fuel, and sufficient type for hydrokinetic energy. Optimal location is selected in 22° in north and 90° east. This is actually the result from the Homer, and which is also downloaded from the NASA's website. The Homer directly downloaded it from the NASA's website. This is the monthly average solar GSI in Manpura Island. There is also clearness index and daily deviation is in the graph. This is actually the wind resource analysis. The graph shows the wind resource analysis, how much wind is available in the Manpura Island. This is actually also given by NASA's website. Monthly available biomass of Manpura Island. This graph is also taken from the Homer software. The input is given by us by calculating how much biomass we can collect from the Manpura Island. This is actually the water speed for Manpura Island, meter per second, and in the x-axis there are months. So this is also from the Homer software. Load profile, as first of all we have selected 17,016 families for this, and we categorize in different categories. So suppose high class, lower class, medium class. First of all, load profile for higher class family. Uh, there is two area, rural area and urban area. Total household for rural area is 98 and urban area for total household is 5. Mainly they use LED, ceiling fan, TV, fridge, mobile phone, etc. The total and capacity is also given here, and total quantity for LED is for the total household 98 is we assume 490, ceiling fan we assume 294, TV 98, fridge 98, mobile phone 294, and average work hours per day. Each everything is LED. Suppose LED is 6, ceiling fan is 14, TV is 4, fridge is 24, and mobile phone is 2. That's how we design. We write design everything. We calculate and give it to the homework software. Give the homework software. Give input to the homework software, and the total power consumption per day in kilowatt is in summer is 5 for urban for rural areas. 541.94 in summer, and in winter 212.66. For urban areas in summer, the total power consumption per day is 27.4 kilowatt, and in winter is 10.65 kilowatt. Load profile for middle class family. This is also this also we have also calculated the total load for lower class middle class family. In the rural area, total household was 247 and urban area is 2. uh, we have calculated we put all the values, and we got that the total power consumption per day is in summer is 912.235 in rural area, and winter is 358.955 kilowatt, and in urban area in summer is 8.65, and for winter is 3.85 kilowatt. Load profile for lower middle class family. The total we put all this value, and we got total power consumption is summer in summer 9,987.75 kilowatt in summer, and 2,530.23 in winter. For urban area we got 138.75 in summer and 35.15 kilowatt in winter. For load profile for lower class family, rural area is about 3045 and urban area is 17. The total power consumption per day is 314.5 in summer and 314.5 in winter. And urban area 1.7 kilowatt, 1.7 in summer and 1.7 kilowatt is winter. We just calculated all this for the only for the households, only for the households. This is then we put all this value in the homework software, and we get the result from we get the result, and it is given in kilowatt. And from this graph we have obtained that maximum load is 2012.6 kilowatt, which is actually in here March, and minimum load is 834.63 kilowatt in December. That is in here. This is the individual monthly load profile, hourly, and it is also shown in hourly. This is for January, this is for February, this is for March, and all the daily profile is shown here in kilowatt hour. This is the schematic of hybrid power plant. We we selected PV system, wind turbine system, biogas generator, hydrokinetic system, and we also need a storage system, suppose battery system and a system converter. There are two buses, one is AC bus and another is DC bus. PP and battery is connected directly with the DC bus, and biogas, then uh, biogas, wind, and hydrokinetic is connected with AC bus line. And converter is between AC and DC bus line. From here we have seen that power consumption, total load consumption is 9,149.87 kilowatt hour per day, and 2112.60 kilowatt is in peak. This is actually the optimization result. This table shows all the feasible combinations of the components characteristics which can satisfy the proposed load demand of the system. Suppose if we select all the six system, suppose PV, wind, biogas, storage, that is battery, wind, and converter, we get the total net present cost is $23.8 million. If we remove PB and calculate with all other system, then we get 26.1 million. That means it rises. If we remove wind, then we get 26.5 million. Again, it becomes greater. If we remove biogas from the system, that the total cost is 71.1 million. That means if we select all the systems, it will be more cost effective. This result is from the optimization table in Homer software. This is actually the cost analysis for this system. If we consider all these things for generic lead acid, battery, generic wind turbine, generic biogas genset, PB, hydrokinetic, and system converter. From the graph we see that the most cost is in the lead acid battery, and then another is in the biogas genset, and lowest cost is in the generic hydrokinetic energy. This is actually the monthly electricity generation in Manpura Island. From here we can see that in March, April, May, June, July, August, September, and October, we get maximum electricity from the biogas. This is actually for the biogas, and second highest was from the wind, and this yellow is from the from PV. Solar PV system output. The generic PV system has a nominal capacity of 315 kilowatt total capacity, and the annual production is 424 megawatt hour per year. This is actually the rated capacity quantity. In the solar system we need total 1347 PB, and rated capacity is 345, which is, as I told before, capital cost is 2.62 million for PB. Capital cost is 2.62 million only for PB, and other things are given here. I am not going through all these. The wind turbine output. This is also from, we get results from the Homer software. This is actually the wind turbine output. Power output from the generic wind turbine system rated at 573 kilowatt, 838 megawatt hour per year. Quantity is 191, rated capacity is 373 kilowatt. Wind turbine total production is 8,38,266 kilowatt hour per year. Capital cost is 3.44 million, Wind turbine lifetime is 20 years. Rated capacity 573 kilowatt. Hours of operation per year is 6,988. Maintenance cost is $34,380 per year. Generic hydrokinetic output. The generic hydrokinetic 40 kilowatt has a total rated capacity of 40 kilowatt, and the total annual production is 3,31,510 kilowatt hour per year. Rated capacity is 40 kilowatt. Capital cost is for $14,000. Maximum output is 40 kilowatt. Hydrokinetic penetration is 9.93%. Total production I told before. Hours of operation is 8,760 hours per year. Levelized cost is $0.00576 per kilowatt hour, and capacity factor is 94.6%. Generic biogas generator. Power output from the generic generator system rated at 500 kilowatt using biogas as fuel is to 2,477 megawatt hour per year. The capacity operational life is 3.95 years. Capital cost is 1.5 million. Fuel consumption is 7,439 tons per year. Hours of operation is 5,057 years per year. Fixed generation cost is $61.3 per hour. Generator fuel is biogas. Generator fuel price is $1 per kg. Maintenance cost is $1,51,710 per year. Electrical production is 2,477,263 kilowatt hour per year. Marginal cost is $0 per kilowatt hour. Advantage of this system is improved reliability. Hybrid system can take advantages of diverse energy resources available at a specific location, which can help to improve reliability of the system. For example, if energy source is unavailable due to weather condition, the system can rely on the other source to meet the energy demand. Increased efficiency. Hybrid system can be optimized to minimize waste and maximize the use of available energy resources. For example, excess energy from one source can be used when demand is higher or another source is unavailable. Cost effectiveness. Hybrid system can often be more cost effective than a system that rely on single energy source, particularly in locations where multiple renewable resources are available. Reduce reliance on fossil fuels. Hybrid renewable energy systems can help to reduce reliance on the fossil fuels, which are a finite and polluting source of energy. Increased energy security. Hybrid systems can provide a reliable source of energy for island or other isolated locations that are not connected to the grid. Implementation challenges. Hybridized power system design and implementation is complex and relatively difficult due to system topology. Insufficient market infrastructure and resources exist to support the hybrid systems component. In remote locations, the maintenance and the availability of large numbers of battery and spare parts can be difficult. The implementation of hybrid system may be impossible without changes to existing laws and regulations, but new one could make it possible. Conclusion. This research combines wind, hydrokinetic, solar, biomass energy sources in order to develop a novel method for storing renewable energy for use in remote locations. Changing from the conventional fossil fuel energy sources to renewable sources of energy such as wind, solar, and biomass is one way to lessen one impact to our environment. Not only does it lack the capacity to meet the growing demand for electricity in rural regions, but it also fails to promote the necessary energy transition in those areas. These research propose a more realistic, grid-connected, non-sales operation mode based on the actual system. This mode has the potential to effectively reduce wind and solar abandonment and lower the impact of system grid connection on the grid. This is the references which I have used in this paper. Thank you everyone. Have a good day.